So usually they're about 12 to 24 carbons. And one of the cool things is that almost all, asterisks, biology always loves to throw tricks at us, almost all natural fatty acids have an even number of carbons in them. You can find one with 12 or 14, but not really 13 or 15. They're almost all even. Just so you're not like on the edge of your seats, because I know this is going to keep you up at night, it's because the unit that they are assembled from is kind of like hooking Lego pieces together, and the unit that they are assembled from in the body is a 2-carbon unit. So when your building block is 2 carbons, it's hard to get an odd number. You have to do weird stuff. So almost all of them are even numbers of carbons. And we have this terminology, which I love and which I think I relayed, maybe it got me kicked out of a store before. I think I shared that story, right? This is where the rage comes in. We talk about fatty acids as being saturated or unsaturated. And again, the word saturated here is referring to saturation with hydrogen. Saturated means no double bonds, the maximum number of hydrogens. 2 hydrogens here, 2 hydrogens there, 2 hydrogens there, all the hydrogens. Everybody gets a hydrogen. Whereas unsaturated would be where we only have 1 hydrogen at each carbon, where we've introduced a double bond. God, no, it's unsaturated. That's as complex as they get. Wow. With one more exception that should be added up there. When we do have a double bond, almost all natural fatty acids have cis double bonds. You'll notice I drew this in the cis configuration. This guy's going down, this guy's going down. I was careful to draw it the right way because in nature, the fats we encounter are almost all going to be in the cis conformation. And that turns out to be pretty important. Because it turns out if you have a trans bond, it's so unique we need a new name. We'd have to call it like a trans fat. And people who say don't eat trans fats and don't know what cis and trans mean, I also yell at. You're not allowed to say trans is bad unless you know what it is. It's like me saying ice cream is bad without ever even trying it or knowing it's made from milk fat that's frozen. Like you're not informed. Stop talking. Okay, so here we go. Here's another picture of them. I have it again, I don't know why. Hydrocarbon tail, fatty group. Yes? A bit, yeah, here. So actually I'm going to skip 2 slides ahead. So this slide, one more. Here we go. Trans versus cis. Let's talk about it because I like food. Most naturally occurring unsaturated fatty acids are in the cis. So sorry. Up here, saturated fatty acid. Down here, cis unsaturated fatty acid. Both naturally occurring. Our body knows what to do with them. Trans unsaturated fats are correlated with things like high blood levels of cholesterol and cardiovascular disease, the American Metabolic Syndrome, and heightened inflammation and arthritis. All bad stuff. Here's why, in the very, very simplistic view, we've gotten to this point in America. So let's tell a story. I like stories, right? I don't know. Maybe they're funny. From about 2000 BC, that's when we first have records of Egyptians and Babylonians baking something with flour and oil, or flour and animal fat that you could call like a cookie. The first cookie was about 2000 BC. And for about 4,000 years, if you wanted a cookie, it was made by mixing ground plant with the fat from a slaughtered animal. That's what a cookie meant. But when mass consumer culture started, that is to say, after World War II, America got out relatively unscathed. Suddenly we were way richer than we knew what to do with. Everyone had wanted to live the lifestyle of the rich and famous. Everyone thought they should be able to go to the store and have a cookie right there ready for them when they arrived. I'm not going to wait 5 minutes or 2 hours for you to bake cookies. When I arrive at McDonald's, you better have a cookie. I deserve it. We're a rich society. Waiting an hour for you to bake a cookie is unacceptable. Just because it's taken an hour to bake a cookie for 4,000 years, this is unacceptable. I want my cookie now. We're really entitled as a culture, right? Like, let's just be clear here. The fact that I can walk in and get a burger in like 3 minutes, and I have to wait 10, if I have to wait like 10, I'm going to write a negative Yelp review. What the hell is wrong with us? Cooking food takes time. Like, this is a thing. Okay, anyway. Okay, there was suddenly this drive to have things like baked goods, like cookies, available all the time. And that had two problems. One, animal fat is expensive. Raising an animal for slaughter, processing it, which is a very polite term for cutting it apart, and shipping the fat and using it is expensive. If everyone wants cookies all the time, we're getting way expensive. And so the first attempt in the 1950s to have grocery stores where you could walk in and just get a cookie was to make them with plant oils. Plant oils are much cheaper. They're still oil. If you bake cookies at home, you'll use plant oils a lot these days. That works. It's okay. We can do that. But it doesn't work in the fast food scenario where you have your cookies sitting under a heating lamp so that no matter what time someone comes in and grabs it, it's a hot, fresh cookie. Plant oil-based cookies under a heating lamp melt. So the solution would have been just be like, we can't give you a hot cookie immediately. You're going to have to wait the 30 seconds it takes us to warm it up. But 30 seconds is too long. So a group of chemists said, what if we could take cheap, plentiful plant oil and chemically modify it to be firm and solid like animal fat? Cis double bond unsaturated fats occur in oils, plant oils a lot. Animal fats tend to be saturated fats. How could I make this look like that? Flip the cis bond into a trans bond. Then chemically they look very similar. And so we invented processes to change this, to take cheap, plentiful vegetable oil and turn it into something like animal fat. And ideally, I mean, let's be honest, ideally the best thing would be to actually turn it into animal fat. To take this double bond and put hydrogens on it. That's the goal, putting hydrogens on it. And so we call this process of putting hydrogens on it. Take some hydrogens, shove them on there. We call that hydrogenation. Take a cheap plant fat, shove some hydrogen on there, you've hydrogenated it. And you've made it firmer, more like an animal fat. It makes a good cookie now. You've made vegetable-based lard. Veggie lard. And here's the problem. If chemical processes were perfect, this would be fine. Take this guy, add hydrogen so it becomes this, we're done, we're good, yay. 100%. But reality has this annoying way of creeping in. It turns out when you have a cis double bond and you react it with hydrogen, by the way, not to like freak anyone out, but the hydrogen here mostly comes from natural gas. So they're injecting petroleum into your animal, plant fats, whatever. Whatever, it's still edible. If they could turn crude oil into a hamburger, I'd eat it, whatever. But to get these to react, you typically need a heavy metal catalyst like platinum. And what's happening on a platinum catalyst surface is that the H2 gets transiently bonded to the surface, and when the double bond comes nearby, the hydrogens get exchanged onto it. Still sounds good so far, except this is a reversible reaction. On your same platinum catalyst, if you have your product come by, it can lose H2. It's a reversible reaction. And unlike a biological system where we have some enzymes specifying cis versus trans, the flat platinum surface doesn't abstract in a chiral manner. You get a 50-50 mixture of cis and trans double bonds in the reverse reaction. And so inevitably, because chemical reactions are reversible, it's like a physical law, when you hydrogenate this, you get some of this as a side product. Oops. And originally, it was seen as a positive. These fats behave very similarly. They have good characteristics. In fact, some would argue they taste a little better. Trans fats taste pretty good. They actually have a little je ne sais quoi. Pretty good, but you should never eat them. They don't occur in nature, and we haven't evolved enzymes to process them. Remember how I said this guy's made of 2 carbon Legos? In the process of fat digestion, we break fats back down into 2 carbon Legos. We break them apart. And we physically actually chew them along. We go gulp, bye-bye, chug, 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 gulp, bye-bye, chug, 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 gulp, bye-bye. We break them down into 2 carbon units, physically kind of walking down the length, cutting it up. The enzymes that do that know how to do that to saturated hydrocarbon chains. And they have a special mechanism to deal with when they reach a cis hydrocarbon. But they don't know what to do when they reach a trans. And so what they do is chomp, 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 chomp. And they undergo a process called enzyme stalling, where the enzyme just sits there. Effectively, this molecule has become a competitive inhibitor. Because instead of chewing up this fat, going on and grabbing another fat and chewing it up, it's just sitting there, not doing its job. And so trans fats slow the ability of the body to metabolize fats.
Can the enzyme ever get rid of it?
It can eventually. It turns out it's a slowdown, but not a complete failure. Eventually, it'll be like, oh, I get it, chomp, chomp. It happens at a rate roughly 10,000 times slower. So it's a pretty big moment. And this is horrible, because look at our American diet now. We have excess sugar. When you have too much sugar, your body turns it into fat. And now, when you have fat storage, like right there, if some of it is trans fat, your ability to lose that weight and get rid of the fat has been inhibited. Because trans fat sits around slowing your ability to work fat off your body. Oops. Especially when you get things like a clog of fats in your arteries. The enzymes there really need to clear that clot before you die. And that 10,000-fold slowdown in clearing that clot is not good. So trans fats are not toxic, except in the sense they are inhibiting your ability to break down fat. And that's not a good thing. Most developed countries in the world have outlawed trans fats to the level of arsenic. Like, you can't have arsenic in your food. You can't have trans fats in your food. The United States is one of the few countries that hasn't outlawed trans fats as a known poison. Like, in the same way that, like, I've had visitors from Germany who are like, this is like saying our product proudly has rat poison in it. Right? Like, we know it is dangerous to human health. And yet, if you go out into our little vending machine out here, half the products have hydrogenated fats in them.
Don't they have to, by law, state that, I mean, they can say 0 grams trans fat,
Yep.
but on the back it'll say hydrogenated.
It has to say
sodium.
hydrogenated, yeah.
So
So if you ever see the word hydrogenated in the label, it has trans fats. Full stop. It tastes so good.
Is there a way, or are they working on a way to do hydrogenation without the reversible reaction, so we could
Yeah.
only do...
So could you get a chiral determinant catalyst? Could you eliminate the back reaction? They've tried. And in fact, you'll see now there's a differentiation. Sometimes you'll see on a label, partially hydrogenated. That means full of trans fats. Versus hydrogenated, which means we got rid of most of the trans fats. But no, there's no perfect process that's cheap and readily available. On top of that, you know, there is a solution that's right there. Use animal fats. Or if you don't want to eat animals, use naturally plant-occurring saturated fats like coconut oil. Unfortunately, now we're destroying rainforests to get enough coconut oil to satisfy them. Shit. It's hard. Being a consumer is hard. Like being an ethical consumer is hard, but it's tricky. What's up? Oh, just stretching. Me too. Okay, so we have these fats. They can be cis or trans. The last thing I really want to talk about today is we probably need some names. There's probably some nomenclature to go with this. And I want to give you the good news. Fats have big, long, complex names, and you don't need to learn a single one of them. Because it turns out fats have so many big, complex names that unlike carbohydrate people who should have fixed their shit like a while ago, the fatty acid community, starting in about the 1970s, said this is getting out of hand. Let's come up with an easy, formal way to do these. And so here's the way we do it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. You count the number of carbons. And by the way, the carbon here does count. This is a carbon. People tend to forget it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And you call this molecule 12. Then you put a colon, and you say how many double bonds it has. There's the name.
Wow, that's awesome.
Only the double bonds between carbons count, yes. Because we assume there's a carboxylic acid. So this happy fellow is 12:0. That's its name. You'll see papers. They'll say, we then mixed 12:0 with this. Like, that's its name. Done. If we have a double bond, 1, 2, 3, 4, well, it's a 1, 2, 3, put it right there. 4, 5, 6, 7, 8, 9, 10, 11, 12. So again, this guy is 12, but now colon 1 double bond. And we have to specify where that double bond is. So we put a delta, and we count from our highest priority group. Carbon 1, carbon 2, 3, 4, 5, 6, 7, 8, 9. 12:1, delta 9.
I've seen people putting C for fatty acids. Like, I mean, that would have been
Yeah.
C9.
Yeah, you can
Or
put
it was
that
trans,
if you
it would
want.
be T9.
Yeah, you can do that. Cis9.
Cis9.
First treat trans 9. Typically though, so that's totally acceptable. In a biochemical context, we typically expect cis, so we don't always specify if we assume that it's going to be cis. But C9 instead of delta 9 is fine as well. Good one. If we had one that had 2 double bonds, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Voila. Here again, we've got 12:2. 12 carbons, 2 double bonds, delta 1, 2, 3, 4, 5, 6, 9. There's its name. Elegant, simple, works every time. Good stuff so far? I only have one wrinkle to add. Here's the wrinkle. Most enzymes in your body that interact with fats bind to this end. It's polar, it's got electrophiles, it's got nucleophiles. It makes sense you can do stuff here. And then like chew down or do whatever. And so the nomenclature system counting from this end makes sense. But there's a small class of very important enzymes in your body that actually grab fats by their tail. And their reactivity is more dependent on what's near the tail than what's near the head. And so we came up with an alternate nomenclature to help us deal with that. And all it is, here's an alternate way, an alternative name for this molecule. 12:1. But if I'm worried about the enzymes that count from this end, 1, 2,